Coming to the last section of this chapter on statistics, I feel like a boy who had been staring at the night sky forever, wondering what was out there into deep space. Then a spaceship comes and it takes him to distant stars, galaxies, nebulas. Throughout this chapter, I describe to you what I saw in this incredible journey where the UFO was none other than Gemini AI. The fourth industrial revolution really happened for me. It did away with the gatekeepers of this phenomenal knowledge that statistics was. I didn't need to go through decades of academia and schmoozing of the so-called professors and guardians of the truth. But in this section, I'm making yet another revelation, like that boy who came back from space in that spaceship would have wondered, would it be possible for me to ever go back there? Could I build my own spaceship? Through this short month-long research, I realized that the answer was yes. And this chapter is the blueprint of the rocket that I myself used to go back to that infinity. To give you an idea of the scale that I'm talking about, think of it this way. Google, Gemini, AI, or as a matter of fact, any LLM is a gigantic rocket that can travel without restraints in the known universe. Then the mini rocket that I have built uses the same principles as the LLM rocket, but it's just tiny fraction of it. It's like a drop of water being the same as the ocean it comes from. But what is amazing is that I found the ocean and I could bring a bucket of it home for keeping. LLM, or artificial intelligence, is the ultimate predictive engine, which is in turn the crown jewel of statistics. It builds on descriptive statistics and inferential statistics. So many things already are dependent on the predictive modeling power of LLM. You don't need to go any further. Look at all your social media apps, the feed and the ads that come are always predicting what you will like to watch based on your earlier online behaviors. Lately in my city, the municipality installed an AI-powered traffic system. At first, we were all skeptical, but ability to predict traffic flow based on the visual input it receives from the various cameras enables it to shorten or lengthen timing for the green light or red light. So sometimes the red light is 93 seconds and other times it is 31 seconds. To a very high extent, the traffic is much smoother after installation of AI in the system of road management. But my point here is not to sing the glories of the industrial revolution of AI. No, I just want you to know that it will create more opportunities like it has for me, I was able to build this mini rocket of prediction, which we will talk about here with one example. This is the ultimate skill for the pilot in the age of the autopilot plane era. I have traveled this road that was unknown. Now, having reached this far in the chapter, you know it. And in this section, you will be equipped with all the skills to have omni data sense. So let us begin. So my mini rocket was predictive engine that could predict whether there would be a traffic jam on a particular day that I was traveling. Before traveling into space with those LLM aliens, I would have left this idea as a fantasy. At best, just for the sake of it, I would have used a random number generator to provide a probability for a traffic jam, just for the fun of it. But with the knowledge of inferential statistics and data analytics that I have now, it's just a piece of cake, you might say. I saw what was in space, and I saw how the rocket was made, and I made one myself. Take a look at the first diagram below, as I will be referring to it throughout my exposition for the next few paragraphs. I have now defined my problem that I want to predict the traffic. So the next thing I had to do was to find the X factors or X features. So I settled on 5 of them, although there could be many more. They were the situations where an accident would occur on the road on that day. Next, it could be a situation where cars were parked in the wrong way on the road on that day. Next, it could be that there was a morning rush, or the weather was bad, or there was road work going on the road on that day. Now that I have the X factors, I needed to collect real data. So I made a team of 100 students who would go on the roads at various times of the day for 30 days. They would fill a form on Google Docs. For every traffic jam they would observe, they would investigate which of the 5X features were present on that day, on that road. Eventually, this produced 500 rows of data or observations. The next step is to embark on the logistic regression as shown in the diagram. So I put this data into Python, see if there is correlation between the 5X features and the Y outcome of traffic. I also want to make sure that their relationship is not a fluke. I also want to know that this whole model of 5X features isn't just noise and useless in terms of signal it produces. Finally, I want to get a weightage of each of the X features in their contribution to a traffic jam. And that would be the formula on which the predictive engine would be based on. My mini rocket allowed me to ask Gemini for the Python code to do the above inferential statistics for my 500 dataset, and the result is the diagram. In the first part, it's saying that the model has converged successfully. The pseudo r squared, which is the error, is which is the measure of correlation, is 0.42. 0.19. This means that the variables explain about 42% of the variability in traffic jam occurrences. And the p-value is a very negligible number, as you can see, nearing 0. It's basically saying that the overall model is highly significant. Finally, it provided the weightage or the coefficient that we call beta required for the equation for each of the 5x features. What the table in the first part is saying is that based on the coefficient analysis, the largest positive effect is from strike accidents. It has put the coefficient as 3.5856. So for every unit of accident, there would be almost 3.5 unit increase in probability of accident. Then as you can see, the p-value is 0, meaning that it's as certain as the apple falling to the ground that every accident will cause some kind of traffic jam. When you look at it from a human point of view, it's so intuitive. In the similar reasoning, the vehicles parked in the wrong way has been assigned the beta value of 2.2 based on the data. For morning rush, 1.7, for weather, 0.22, for roads, minus 0.022. Looking at the p-values, we notice that in the case of the rain, it is 0.52, which is greater than 0.05. What it is saying is that even though the rain has a small contributing factor to the traffic jam, most likely random. In part 2, you can see that there is a feature correlation or chi-square test provided for accident or strike versus traffic jam. This is just an example. As you recall, the chi-square is used when the two datasets are of category data nature. You can see the value is 149.8, which is a high value. It means that there's a strong correlation. The p-value is 0, as we have discussed earlier. Then using descriptive statistics, the contingency table or observed counts is telling you that in 341 data entries where there was no accident, there also was no traffic jam. However, in 45 rows, despite there being an accident, there was no traffic jam. Then, during 45 data entries where there was an accident being reported, there was actually no accident reported. And in 78 cases where there was an accident, where a jam was reported, there was an accident. So what this table is saying is that there is a high correlation between traffic jams and accident or strikes. Whenever there is a traffic jam, there is double the likelihood it was caused by an accident, or at least there is an accident nearby. And only in 10% cases where there is an accident, there is no traffic jam. The next step is to do a model performance or F1 score confusion matrix test. So basically, we test all the 5 features at once, see if the means of the 5x factors produce noise or signal. The F1 score we got was 0.6699, which is a very strong score for this type of relationship. Then the confusion matrix is something very interesting. It basically tests the 500 data against the logistic regression formula that we made from this model. So at this stage, the predictive model is testing itself against itself. It assumes that all the 500 data are new data, then it runs the model for each of them. And the confusion matrix is the output. As you can see, 2 by 2 matrix. Let's start with the combination of a jam was predicted by the model, but it did not occur. That's called a false positive. The data of 500 we had produced 14 of them. Then the second quadrant, as you go anti-clockwise, is telling the number of cases where the jam was not predicted and there was actually no jam. There are 363 such true negatives. Then the third quadrant is when the jam was not predicted but actually occurred. It's called false negative, and there are 54 of such cases. Finally, the situation where the jam was predicted and there was actually a jam is called true positive, and there are 69 of them. Now, based on this, we get to the fourth part of the predictive engine, called the simulated rerun or weighted adjustments. It uses the concept of mean absolute error or MAE, and based on the confusion matrix that we discussed earlier, the predictive engine running on Python here made an adjustment in the weightage for the 5x features. As an example, the weight for parked wrongly was initially 2.2668, but after the simulated adjustment based on the real-time MAE minimization that we just did, the engine adjusted the weight to 2.2441 for the same X feature of parked in the wrong way. This has been done for all the other 4 X features, and the commercial system successfully begins iterative weight deployment using the initial model, how it can be deployed. So all of this exercise leads to the resulting formula that we will be using in this predictive model. Refer to the second diagram below. First box, D1, is showing how the formula is derived for our predictive engine. First calculates the log odds or the linear predictor LP. This is the weighted sum of all the factors. Remember the coefficient that we changed after the simulated adjustment and confusion matrix? They are the weightage or the beta in the diagram. We have to use the baseline weightage, and it's known as beta 0, that we add beta 1 into x1, beta 2 into x2, and so on. And then we get the final formula for linear predictor LP, as shown below, is equal to minus 4.1858 plus 5.5856 times accident and strike plus 1.7708 times morning rush, and so on. Now, what we want is a probability of traffic jam. That is obtained using formula shown. This converts the log odds into a percentage of probability between 0 and 1, which is exactly what we want. It produces a sigmoid curve shown in D2. In the x-axis, you have the linear predictor LP, and in the y-axis, you have the predictive probability of traffic jam. As you can see, for every yes in the X features, the sigmoid curve is shown to increase. It starts from 0 probability, where all the features are not happening. That means that there is no accident or morning rush or cars parked the wrong way, no road work, the weather is good, and there is no road work. Then you can look at the table below. It shows all the combinations of the X features. What it's telling is that if only accident occurred, then the probability shown by the sigmoid curve would be 35.43. Then if you add to it the morning rush, you would have to add 8.2% and so on. Then in terms of combinations, when there is a parking problem and it's rush hour and it's also raining, then the sigmoid curve gives a probability of traffic of 52%. Then the last row talks about a situation where all the 5x features are concurring at the same time on the same road. In that case, the probability shown by the sigmoid Freud would be 97.51. You'll notice that it's not 100%. That is obvious and intuitive because there are many other factors that we have not considered here. So we are just leaving more possibilities open. The beauty of the sigmoid curve is that it allows that. And the situation where we would collect 500 real-time data after deployment in the monitoring stage. So it's showing the table of the original coefficient versus the revised coefficient as per the mean absolute error, or MAE, that Python calculated, saying that there are either false positive or false negatives 17.42% of the times. So the proposed revised new formula would be shown with the new revised coefficients. However, in real life, table below shows 3 types of MAE scores and the corresponding actions required for them. When the threshold, that is MAE, is less than 0.18, it's called optimal and no action is required. Performance is within tolerance and considered statistically stable. All we need to do is continue routine monitoring and data logging. The error is very mild noise which can easily be ignored and should be ignored. So because our MAE score is 0.1742, which is in the optimal level, we take no action in real life. So it means that we keep the old formula for predicting traffic. However, if the MAE value was greater than 0.18, less than 0.2, then that would be a warning. We would need to investigate, that is, review new data features for outliers, missing values, or shifts in factors' importance. We'd also need to prepare a backup dataset for potential retraining. This is the first sign of what we call data drift. Third level is the critical one, where MAE is greater than 0.2. Action required is mandatory update. You have to immediately halt the new model prediction possible and execute a full retraining using all historical data and new data collected to date. This ensures predictive reliability is restored before major losses occur. Now we have built the model and its skeleton and the various systems that's required to keep it alive. The next step is to put some skin on it. So this is shown in the diagram below. Again, using Gemini AI, I produced a React code that provided the app as shown in the diagram. In the first part, the user clicks on the X factor features. Here I clicked yes for weather, peak hour, and road work nearby. Then You have to press on the calculate probability. The score 30% came as per the sigmoid curve that we discussed earlier. Then I pressed on the green button for the sake of finding the error in the future studies. It just asks you if the traffic jam actually occurred or not, and you would feel that afterwards. Here I clicked no. At the bottom you can see that the app returned an MAE score of 0.3. You might be wondering if this is just a gimmick. Actually, no. What I did was use Gemini chatbot as the backend, as shown in the architecture of this app. Then I used this backend or Gemini chatbot to create a database in Firebase, which is a free version of SQL. It was needed to store all the data that would be produced. And this same backend or Gemini chat bot was used to link with Gemini API. This is where the formula that we developed was enhanced. It used the same coefficient but adjusted them as needed by allowing for more options in the future, like duration of the accident or strike, number of car parked wrongly, and so on. And Gemini API also was used to provide reasoning for the probability score. That's again a predictive engine function, but because I use Gemini API, I did not have to do it myself. Reasoning in our example was provided as the 0.05 baseline increases by 0.25 due to bad weather and road work, but receives no additional increase because it is not a commuter per day peak hour and no nearby event is scheduled. So by using Gemini API, I could achieve more than by just using Python. Finally, Gemini chatbot produced the front end that you are seeing. My mini rocket went beyond the Earth's gravity into space. I'm showing you a few stars up close. But you might be wondering that we actually have not left the ground. We're just watching a movie of the stars. So to answer this objection of yours, we looked at G4 diagram below. It shows a deductive area calculator that I made again using Gemini AI. What I do is put the radius, then click calculate area, and it provides me the area, which is here 206 for a radius of 8.1. And just for the sake of consistency, I asked it to produce the mathematical error versus MAE score. Obviously it is 0, as the area is precisely calculated using geometric definitions, that is A is equal to pi r square. This result is a mathematical certainty derived from axioms and of Euclidean geometry. So no, I really went out of space, crossing Earth's gravity. It's not just a TV show. By referring to the table in G4, you can see the origin of a descriptive formula like the area of a square is derived from geometry and axioms, whereas for a predictive model, which uses logistic regression, origin is derived from historical data. The model learns itself. Purpose of the descriptive formula is to define a known truth, whereas the purpose of a predictive model is to estimate an unknown event in the future. The era error in the discrete formula is always 0 unless you measure the radius wrong. But in the case of predictive model, the error always has some error. It can be wrong. So it's basically deterministic model versus probabilistic model. So the reasoning type used to calculate the area is deductive, while to predict the traffic is inductive. I know what you might be feeling. It's just too good to be true. Well, not that I'm bragging, but what I have done is experiment using the same principles I used in a giant project. To be more specific in my analogy, I did the Faraday's law experiment, shown as G5, where I put a copper coil around a pipe and push a magnet in it and put it out consecutively. In this way it produces current. This works. At least I know it works because this was a project that I did when I was in grade 9 in school. This is the mini rocket that I built and I showed you. Same principle applies for a gigantic hydropower plant as shown above. You have to build huge dams, pipes and turbines and so on. Essentially, no matter how big it is or complex it is, it still follows the same Faraday's law that I applied in my project work in high school. So my traffic model used the principle of statistical learning, that is, finding patterns in data. The tool it used, like the simple wire and magnet, was logistic regression. My system learned from linear patterns here. Obviously, a hydropower plant is much bigger. Similarly, social media feeds we discussed earlier use neural networks to learn from complex nonlinear patterns. It's nothing more than an expansion of the logistic regression. There's difference in magnitude. Hydropower plant would need engineers, structural engineers, dynamics, so on. Similarly, for a big engine akin to artificial intelligence would require much more data in the scale of trillions and gigantic computing power or GPU clusters. Move from linear to nonlinear to multidimensional parameters and so on. Fundamentally, principles that they use is the same one that I used in my traffic model. And if you have understood this far, then you too can build your mini rocket and see the universe with your own eyes. Summarize how I built and you can build this mini rocket. I refer to G6, which shows the 5 steps of building a predictive model. It is common for building a mini rocket like we did, and to build gigantic ones like the one used by Amazon and social media feeds, or by the police to identify fingerprints of criminals, or by Microsoft or Google recognize our handwriting. What we did at the first is, after defining the problem, is to collect the data and cleaning it. In our case, which was low chaos, we collected a small data of binary traffic features, here 500. In the case of high chaos, like the feeds, those advanced models collect terabytes of high frequency sensor data. In the case of advanced models in other fields, they might use satellite imagery and even weather patterns as input data. Second step is the feature engineering, where we select or create the best variables for prediction. Our model, we just use the 5 given inputs as is simple direct features. In the case of advanced models, we need to engineer complex features like the rate of speed of change or localized humidity gradients. Basically, we'll have to invent along the way to predict the outcome and minimize the MAE as we go along. Third step is model selection, where we choose the right algorithm for the problem type. In our case, it was logistic regression. It was simple, linear, and interpretable. In the case of high chaos advanced models, we'd use recurrent neural networks or RNN transformers used for complex nonlinear data, and they can handle sequences which our model can't. The fourth step is training, to allow the algorithm to learn the relation between the features and the outcomes. As we learned in the simulation and the confusion matrix, the algorithm finds the 5 optimal betas or coefficients. In the case of advanced model, the algorithm adjusts millions of interval weights and biases across many layers using mainly calculus and optimization mathematics. The final fifth step is evaluation, where we test the model's accuracy and generalization on unseen data. Here we tested against 500 new data to calculate the mean absolute error, MAE, and accuracy. In the case of advanced model, it would not be sufficient, and we need to calculate the F1 scores, precisions, and recall, often requiring complex metrics to handle false positives and negatives. We have reached the end of this section and this chapter. The boy who stared at this space, dark of night, now his own rocket. I have tested it, it works for me, and I have come back to tell my tale. Even though in this section I built a mini rocket to predict traffic, so those aliens showed me around the universe in the gigantic rockets. I have many more predictive models pipeline. Among them is Dream Materialization Predictor. The app will feature a box where the user will write his dream, and based on the thousands of historic data from my own diary and the subsequent day diary, I would use Google Gemini API, make a predictive model, most likely based on neural networks, to predict kind of day user will have on entering his own dream. Might sound crazy, but you have seen throughout the section, principle is the same. It's just the scale that is different. Like today's law applies in my project as well as in the Niagara Falls power generator. I never thought that statistics took me to outer space, but it did. Ultimate fruit of statistics is indeed predictive modeling or advanced data analytics. I've been saying throughout this chapter, this has equipped us humans with omni data sense. Hope that this chapter will serve you as a motivation to explore more in this magnificent subject of statistics. At least I hope that you will begin to love this subject as it should be loved.